Thank you, Dr. Stephen Kane. Thanks for accepting this interview. It's our pleasure, and people who are viewing this interview would be very happy. It would be inspirational for them. Uh, before going to questions, may you please give a very brief bio about your background and where you started astronomy, especially when you were a kid.
Sure. I became interested in astronomy when I was very young. It was between the ages of about 10 and 12. 10 was when I really became interested. And I grew up in outback Australia where there was very little light pollution. And so the skies were very dark. It was the southern hemisphere, so it was many, many stars. And it was when I was 12 years old I went to a planetarium, and that was really where I became completely hooked in understanding stars, mostly understanding planets. I was very interested, particularly during the 80s when I was a teenager. There was a lot of missions to the outer planets of our solar system, and I was very interested in the results from those, the close-up views of Jupiter, Saturn, and also Uranus and Neptune. So that's when I became very, very interested. Then I started doing my doctoral philosophy in about 1995, and at that point we just started to discover planets and planets around other stars. So I thought, well, okay, well, here's an opportunity to study an infinite number of planets rather than just the ones in our own solar system.
Okay, thank you. Here are some questions from two astronomical groups. One of them are in north of Iran, the other one is in the south of Iran. Let us start from the Sagheb Astronomical Association questions. The first question is that how do you detect exoplanets?
So detecting planets is very, very difficult, which is why we haven't done it until recently. Because one of the things I always say about discovering exoplanets is that it's one of those areas of science where technology had to catch up to ideas. Because people have been talking about planets around other stars for literally thousands of years. You can trace this all the way back through the written record to the Greek philosophers, thousands of years BC and before that. So this is not a new idea. We just couldn't do it. We didn't have the means to do it. So why is it so hard? The reason it's so hard is because you're trying to discover a small object next to a large, bright object. And so for that reason, trying to directly discover a planet is especially hard because the planet is very faint, but the star is very bright. So what we tend to do is we rely on what we call indirect methods. We don't see the planet directly, but we observe the effect that the planet has on its surroundings. And that includes a gravitational effect. Sometimes it can block the light from the star it's orbiting, those sorts of things. And so the methods which have been used so far have been primarily the gravitational effect of the planet on the star, which causes the star to wobble. So that even though we can't see the planet, we can see the star, we can see it wobble. And secondly, if the planet passes between us and the star, then it blocks out some of the light. We call that transit method. And so if we can measure the brightness of the star very, very precisely, then we can observe that effect. Those are the two main ways. There are about 6 or 7 techniques. Almost all of them are indirect methods, but the transit method and the wobble method are the two main methods.
Thank you. The next question is, how do we know these exoplanets are similar to our Earth and they would possibly be habitable?
Yeah, that's a difficult problem to try and solve, and it's of course what we really want to solve, because this is all about answering this question about how common is life in the universe. So first of all, how do we know it's similar to the Earth? the first thing we do is we measure, from those two techniques I just mentioned, we measure the size and the mass of the planet. And especially the size can tell us if it's the same size as the Earth. And we are discovering when does something stop being a rocky planet like the Earth and start being a gas planet if it becomes too large. So we use these measurements to determine if it's rocky, like would it have a rocky solid surface like the Earth. So from those techniques, we learn that part. As to whether it's habitable, that's far more complicated because one of the planets I study in great detail is right here in our solar system, Venus. And Venus is pretty much the same size and mass as the Earth, but is completely hostile. So obviously knowing the size and the planet alone is not enough. You need to know more. And so what we do is we create models of the atmosphere based on how far away the planet is from the star, how much energy it's receiving. And what we're hoping to do in the coming years with the James Webb Space Telescope is to obtain measurements of these atmospheres so that we can test the composition along with how much energy the planet is receiving and put all these together into a self-consistent model so that we can determine whether the surface might be habitable or not.
Thank you. Next question is a bit philosophical. What is the benefit of discovering these faraway extrasolar planets? Are we looking for a kind of self-satisfaction or?
I really like this question a lot. It's a question that many people, many of my colleagues occasionally get this question and they're terrified of it. It's worded in different forms. Like, for example, someone might say, why do we even spend any money on astronomy when there's so many other societal problems that we should be dealing with? So there's a couple of things about that. One is that there will always be societal problems. Like, as soon as we solve one, we solve another. Like, I was talking to someone the other day saying, well, it's more important that we address global warming. And of course, once we address global warming, then of course you're going to say, well, there's these homeless people over here. What are we going to do about that? And the schools are falling apart. I mean, so the trouble with that line of reasoning is that it's looking for a practical application. In other words, how will learning about the stars and the universe, how will that help me pay my bills? How will that help me fix my car that needs repairs? How will it help these people who are over here who are hungry? That it's the wrong line of reasoning, completely wrong. Because the reason that we do astronomy is all about culture. It's not about how will it benefit society in terms of feeding people and doing that sort of thing. It's about how do art museums help society? How does music help society? How do other disciplines like archaeology, learning about our past, how does that help society? You know, there's societal health. And this is something that people sometimes miss when they ask this question. Societal health is more than just people having jobs and all those kinds of things. It is the cultural aspect that makes us human. And it's that human desire to want to be better than we are. You know, we want to rise to something better. So as you said, it's a philosophical question and therefore it has a philosophical answer. And the reason that we do this about looking for life in the universe is to tell us our place in the universe and to understand that we are a part of a much bigger picture. Yes, there are issues that do need to be solved. One of the arguments that's often made is that, well, if you look at the amount of money that goes to NASA, it's essentially nothing compared to the amount of money that goes to the military. So you need to be able to prioritize things. But if the argument is that we shouldn't spend any money on astronomy, art, music, archaeology, all these other things, and if we just removed all of that, can you imagine what that would do to societal health? Societal health would collapse. It would absolutely collapse. And so that's why I'm so passionate about this subject. I think it's so important for societal health as a whole in understanding. I mean, like I mentioned, right now in history, for the first time, we can actually answer a question that philosophers 3,000 years ago had no capacity to answer. They could only speculate. That's quite a big deal, and quite a jump forward. And it's something that I think we should all be pretty excited about.
Yeah, thank you.
That was a very long-winded answer.
The next questions are more tangible. How can we take a photograph from an exoplanet?
You mean take a photograph of an exoplanet? Or?
Yeah.
Yes. So, like I mentioned at the beginning, taking a picture of an exoplanet is very, very difficult. Usually what we do is we look at the effects that the planet has on the star or something like that. But we can do it. We can do it because we can use special techniques to try and block out the light from the star it's orbiting. And if you can do that, then you'll start to see the planet. It's very difficult to do from the ground, especially because we're looking through the Earth's atmosphere. And the Earth's atmosphere has this distortion effect that makes that kind of process difficult. And so usually if we're trying to take a picture of an exoplanet, we need to do it from space. And so this is why there's plans now over the next 10, 20 years to develop space-based missions specifically for taking pictures of exoplanets.
I assume the person who asked this question means how he can take a photograph from primary tools like a camera or like something like this. So according to your statement, it's not possible.
Well, this relates to, I know there's a later question about how can other people be involved in that sort of thing. So, yeah, so we can talk more about that.
What is the biggest exoplanet ever discovered?
The biggest exoplanets are the easiest to discover because they have the biggest effect. They block out more light, they cause the star to wobble more. So the biggest planets are the ones that we found first, and the biggest ones that we have found are around about twice the size of Jupiter. If you get any larger than that, by the way, then it stops being a planet. Usually if you have much larger than Jupiter, maybe even just 50% larger than Jupiter, it will start to become a different type of object. And obviously if you keep increasing the mass, you're talking about a star then, or a brown dwarf rather than a planet. So the biggest planets that we found in terms of size are around about twice the size of Jupiter. In terms of mass, probably about 20 times the mass of Jupiter.
Okay, thank you. Now, let me ask you a kind of imaginary question. Can we, instead of studying other planets, just change the place of Earth with the help of some kind of micro black holes or an array of them, and let these black holes pull the Earth, change the place of Earth, and then study them?
Yeah. So one of the important things we have to remember is that things have not always been as they are right now. We are living at an age of the Earth of about 4.5 billion years. That's not only true for the Earth, that's also true for Venus, Mars, and so on. What this means is that if we want to study different kinds of planets, there is a way that we can do that without having to create black holes, which sounds incredibly dangerous, I have to say. We can study the Earth and Venus and Mars as a function of time, because Earth has changed with time. My colleague here at UC Riverside, he often describes it as alternative Earths. If you think about the Earth when it was 1 billion years ago, 1 billion years old, then it wouldn't have had oxygen in the atmosphere. It wouldn't have had any or most of the kind of life that we now currently have. It would have been a very different kind of planet. So we can look at that as a prototype of an exoplanet. That's a different kind of planet if you just look at Earth at different parts of its history. It's also true of Venus, because Venus is now this cloud-covered, post-runaway greenhouse hellscape, but it wasn't always like that. And the models suggest that only about 1 billion years ago we could have had liquid water on the surface. If there was an alien civilization that looked at our solar system only 1 billion years ago, they probably would have concluded there's at least 2 habitable planets in that system and possibly a third, talking about Mars. So that's quite interesting, right? Because you realize then that each different stage of evolution of the solar system represents a completely different kind of set of planets. So I think that's the best approach to doing this. If you want to say, well, how can we use the solar system to emulate different kinds of exoplanets? All you need to do is just look at what we've learned about the history of Earth and Venus in particular.
So you recommend not changing the Earth's place, just study other alternative?
I recommend against spontaneously generating black holes in the vicinity of the Earth.
Now, external questions from south of Iran, astronomical group from Bushehr. The first question is that what kind of affordable projects can independent astronomical groups do about extrasolar planet? Is something like photometry possible, which is the most...
Yeah, this has been really interesting because it's something which has become far more accessible, which is that you can now buy off-the-shelf commercial CCDs for telescopes, which can achieve the kind of precision on photometry that's needed to discover new planets. And indeed, people have been doing this for quite some time. There are, I know that some of my colleagues do collaborate with networks of amateur astronomers who do collect data and upload it to a central website. Somebody who's leading the project may say, oh, we think there might be something interesting happening with this star, everybody look at it. And so different groups of amateur astronomers will use their equipment to look at that, gather data, upload it, and some planet discoveries have come out of this. This is generally referred to as citizen science. It's just when the general public gets involved in this exciting endeavor of finding planets around other stars. So particularly for transiting planets, that is very accessible, and that's something which is ongoing, particularly with new space missions which are discovering planets around other stars. Oftentimes we rely on networks of amateur astronomers to provide additional data for those discoveries. And I can give you some information about that to pass on to people about how they could get involved in that.
So hopefully there's some project. Next question is, may you please introduce some online resources we can access data gathered from other telescopes around the world for extrasolar?
Yeah, and that's a nice follow-on from what I was just talking about, because as well as these websites where amateur astronomers are uploading their data and making them available, there are also a lot of data archives now. There's been a number of exoplanet missions like the Kepler mission and now TESS, but these data are all required to become public because these are publicly funded missions, and so the data really belongs to everyone. And so has been an evolving strict policy about making data public. That wasn't always the case, by the way. You only need to go back a decade or several decades to find an era where scientists were hugging their data to their chest and protecting it and weren't releasing it. That is no longer the case. We now live in a global network. The internet has enabled accessibility of the data, and there's a lot of it. And far more data than individuals can process on their own, and so it's in their best interest to make it available so that other people can look at it. And once again, I will provide you with links which you can pass on that have all the data that people would ever want.
So let me give me a comment. According to the believe of lots of people working on astronomy or extrasolar planet or anything related to astronomy is just doable by telescopes or big facilities. But as you said, if you know how to program, how to analyze the data, you can do lots of great things.
Yes, that is absolutely true. The data from the large telescopes are publicly available, but yes, that is not all of the picture, because oftentimes the stars are too bright to use large telescopes. This is one of the misconceptions, by the way, with astronomy, and I'm sure the amateur astronomers who are watching this know this, which is that people assume that the bigger the telescope, the better.
Yes.
Like if you have a much larger telescope, you can do far more than you can do with a small telescope. Not necessarily true. A larger telescope simply means that you can observe fainter objects. That's what it means. But if you're observing a bright object, you can't use Keck to look at a bright star. I mean, it's not that you shouldn't do it, you probably shouldn't, but you actually can't, because you're saturated in less than a second. So there is an enormous need for the small telescopes and in particular the amateur community to contribute to this.
So that's good news. Next question. How do you see the future of space missions to habitable extrasolar planets?
Yeah, I had mentioned earlier about the plans for missions over the next 10 or so years to directly image planets. I think that's really where this is going. At the moment, we have discovered around about 4,000 planets, and some of my colleagues who are not exoplanet folks, and even some who are, have made snide remarks that exoplanets is now essentially becoming stamp collecting. You know, if you have 4,000 planets, why is one more interesting? There's a couple of answers to that. One is that even though we have 4,000 planets, we're only really now just delving into the area where they're small and like the Earth, so that's interesting. But once we discover, 1,000 planets the size of the Earth, what then? Is it still interesting? What are we doing next? And the answer is that we're doing the atmospheric characterization, we're doing the direct imaging. That's what's coming next. And so that's what's leading the next generation of space missions, which is what telescopes do we need to launch into space in order to be able to not only detect the atmospheres, but infer what's going on at the surface, and in particular, be able to infer if there's biological activity, what we refer to as biosignatures. And this is really the end game of this whole process of trying to detect evidence that there is life on a planet that we've discovered. So that is the focus of missions that are coming over the next decade or two.
Okay. Thank you for answering all of these questions. If you have anything to say to the audience.
Just that it's been a real pleasure answering your questions. I've really enjoyed it. They were great questions. If you had any more questions, I'll be happy to do this again sometime. But I hope you've enjoyed watching this, and I hope to do this again sometime.
Okay, thank you. Thank you for your time.
Thank you.
Thank you.